We present our work on real-time cooperative distributed model predictive control for embedded systems. In this work, we focus on the formation control of hovercraft. Each hovercraft can produce thrust in every direction, allowing them to move freely on an air hockey table. The hovercraft are each equipped with racing drone hardware and a Rexa 03W for onboard computing and Wi-Fi communication. Thus, we can test and execute our algorithms off-board on workstations or onboard the embedded processor. The distributed MPC controllers collaboratively solve a centralized optimal control problem in each time step to plan optimal trajectories in real time. Apart from external position measurements, the implementation only requires neighbor-to-neighbor communication. We combine the well-known real-time iteration approach from centralized MPC with a tailored SQP method based on ADMM. In each sampling step, the method linearizes the optimal control problem, and the resulting QP is solved using decentralized ADMM. As you can see, ADMM converges to the QP solution. The real-time iteration scheme uses a warm start from the previous time step and thus approximately converges to a local minimum of the centralized OCP. In this particular example, you can see that we can avoid collisions due to non-convex minimum distance constraints. Here, the blue hovercraft follows a pre-planned trajectory with other hovercraft forming in chain formation. Additionally, we have a separate hovercraft acting as an obstacle, which the others are trying to avoid. To avoid a collision, the hovercraft have to dynamically adapt their trajectories. Once the obstacle has passed, the hovercraft continues tracking the pre-computed trajectory. In this example, the trajectory of the obstacle is not known. The hovercraft have to dynamically replan their trajectories in real time. Note that the others are slowing down to keep the formation due to the middle hovercraft dodging the obstacles. Formation changes such here from a line to a square can be planned and executed on the fly. In the next experiment, the hovercraft swap positions. This shows the cooperation. The hovercraft have to negotiate and compromise their direct paths to avoid collisions. In all the onboard experiments seen so far, the ADMM iterations were kept at 2 iterations per step, allowing for fast sampling but potentially poor solution quality. By tripling the sampling interval, we can also triple the ADMM iterations and thus investigate the trade-off between optimized accuracy and sampling interval. Here, a faster control sampling yields better performance. Note that the iterations are limited by relatively high Wi-Fi latency and not by the online computing power. To summarize, we implemented cooperative distributed MPC for hovercraft formation control with dynamic obstacle avoidance. The controllers execute in real time both in off-board and on-board experiments thanks to our tailored decentralized optimization algorithms.